This is a presentation on real number system. This is a presentation on real number system. The set R of real numbers consists of rational and irrational numbers. The set R of real numbers consists of rational and irrational numbers. Now, let's look at a rational number. A rational number is any number that can be expressed as a quotient or fraction of two integers. A rational number is any number that can be expressed as a quotient or fraction of two integers. Now, if R is a rational number, then there are two integers, a and b, such that R equals b over a, such that R equals b over a, where a is not equal to 0. Where a is not equal to 0. Because if the denominator a is equal to 0, then R equals b over a ceases to be a fraction, ceases to be a rational number. And so, if R is a rational number, then there are two integers a and b, such that R equals b over a, where the denominator is not equal to 0. Where the denominator is not equal to 0. Now, let's look at types of fraction. Now, we look at types of fraction. The first type we are going to look at is the proper fraction. The first type we are going to look at is the proper fraction. Now, given the fraction R equals b over a, the number or the variable above the division sign is called the numerator, and the number or the variable below the division sign is called the denominator. Now, if a fraction is proper, if you have a proper fraction, then it means that the numerator b must be less than the denominator a. So for proper fraction, b is less than a. That is, the numerator is less than the denominator. b is the numerator and a is the denominator. Now, these are examples of a proper fraction. 2 over 3 is an example of a proper fraction because the numerator 2 is less than the denominator 3. 1 over 2, that is half, is also a proper fraction because the numerator 1 is less than the denominator 2. 4 over 9 is also a proper fraction because the numerator 4 is less than the denominator 9. So these are all examples of a proper fraction. These are all examples of a proper fraction. Now, improper fraction. Improper fraction. So given R equals b over a, where b over a is the fraction, b is the numerator, and a is the denominator. For improper fraction, the numerator is greater than the denominator. The numerator is greater than the denominator. So b is the numerator and a is the denominator. Now, example, 5 over 3 is an example of an improper fraction because the numerator 5 is greater than the denominator 3. 11 over 8 is also an improper fraction because 11 is greater than the denominator 8. 12 over 5 is also an improper fraction because the numerator 12 is greater than the denominator 5, etc. So these are all examples of an improper fraction. Now we consider the mixed fraction. Now with a mixed fraction, we have a whole number together with a fraction. We have the whole number together with a fraction. So if R equals a whole number b over c, a whole number b over c, a whole number b over c. Example, 2 whole number 2 over 3, 4 whole number 1 over 2, 3 whole number 4 over 2, etc. These are all examples. These are all examples of mixed fraction. 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 Now let's look at how we can convert mixed fraction into improper fraction. Now let's look at how we can convert mixed fraction into improper fraction. So given the mixed fraction, say R equals A whole number B over C. A whole number B over C. Then how do we convert this mixed fraction to improper? First, we multiply the denominator of the fraction by the whole number. So we have C times A, in bracket, C times A. Then we add it to the numerator of the fraction, that is plus B. Then we divide the results by the denominator of the fraction, that is C. So converting A whole number B over C to an improper fraction, we multiply the denominator of the fraction by the whole number. Then we add the results to the numerator. Then we divide the results by C. So we have R equals C times A. That is C times A. Plus B. That is plus the numerator of the fraction. All divided by C. That is the denominator of the fraction. Example. Given 2 whole number 3 over 2. How do we convert this to improper fraction? We multiply the denominator of the fraction by the whole number, so 2 times 2, and we have 2 times 2 in bracket, plus the numerator, that is 3, then we divide by the denominator of the fraction, 2. Now 2 times 2 is equal to 4, and 4 plus 3 will give us 7, so we have 7 divided by 2, so we have 7 over 2, and this is an improper fraction, because the numerator 7 is greater than the denominator 2. So 2 whole number 3 over 2 is equal to 7 over 2. Now let's look at irrational numbers. Irrational numbers are numbers that cannot be expressed as a quotient of 2 integers. It means that irrational numbers cannot be expressed as fraction. Irrational numbers are numbers that cannot be expressed as a quotient or fraction of 2 integers. Example, we have pi, square root of 2, square root of 3, square root of 5. These are all numbers that cannot be expressed as a quotient of 2 integers. These are examples of numbers that cannot be expressed as a quotient or fraction of integers. And so they are called irrational numbers. Now, approximations. We consider decimal places. Decimal places refers to the digits on the right of the decimal point. Decimal places refers to the digits on the right of the decimal point. The number of decimal places is the number of digits after the decimal point. The number of decimal places is the number of digits after the decimal point. Now let's consider these examples. A, 46.765. We have 3 digits after the decimal point, and so 46.765 is in 3 decimal places. Now B, 23.65. We have 2 digits after the decimal point, so 23.65 is 2 decimal places. Now C, 18.7. We have only a digit after the decimal point, and so 18.7 is in 1 decimal place. Example, correct 9.4268 to A, 1 decimal place, B, 2 decimal places, C, 3 decimal places. Solution: A, 9.4. 9.4. Now when we correct 9.4268 to 1 decimal place, the answer is 9.4. Why? This is because when you consider the number 9.4268, it's in 4 decimal places. So if you are to correct this number 9.4268 to 1 decimal place, then we count the digit after the decimal point. So 1. So it's supposed to be 9.4. But take note, you have to consider the next number to see if it is equal or greater than 5. then it is considered as 1 and added to the digit. So 9.4, now when we consider the next number is 2, and 2 is less than 5. So we ignore the numbers, and so we have 9.4. That means that 9.4268 is equal to 9.4 corrected to 1 decimal place. Corrected to 1 decimal place. Now B, 2 decimal places. 9.4268 to 2 decimal places. So we start to count after the decimal point. So 1, 2. 1, 2. So it's supposed to be 9.42, but the next number is 6, and 6 is greater than 5, and therefore we consider it to be 1 and add it to 2. So 1 plus 2 will give us 3. So we have 9.43, and that is how come we had 9.43, and this is corrected to 2 decimal places. This is corrected to 2 decimal places. 9.43. Now C, 3 decimal places. 3 decimal places. Now we have 9.4268. So after the decimal point, we start to count. We have 1, 2, 3. But the next number is greater than 5, and therefore we consider it as 1 and add it to 6. Now 1 plus 6 will give us 7. So we have 9.427. And that is how come we had 9.427. 9.427. Corrected to 3 decimal places. Corrected to 3 decimal places. Corrected to 3 decimal places. So we have 9.4, that is corrected to 1 decimal place. We have 9.43 corrected to 2 decimal places, and we have 9.427 also corrected to 3 decimal places. Now example, correct 3.795 to 2 decimal places. Now the number is 3.795, and so because we are asked to correct to 2 decimal places, we start to count after the decimal point. So we have 1, 2, 1, 2, but the next number is 5, and 5 is equal to 5, and therefore we consider it to be 1 and add it to 9. Now 1 plus 9 will give us 10, so we write 0 and add the 1 to 7, giving us 8, and so we have 3.80, 3.80, 3.80 corrected to 2 decimal places. Corrected to 2 decimal places. That is, we have 2 digits after the decimal point now. So we have 3.80 corrected to 2 decimal places. Significant figures. Significant figures refers to the number of digits in a number. This excludes zeros, holding places at the end of a number or at the beginning of a number. This excludes zeros, holding places at the end of a number or at the beginning of a number, to the right of the decimal point. Now let's take a look at these examples. Correct to 3 significant figures. I, we have 0.0006875. II 63429.71. Now solution. I, we are given 0.0006875 to correct to 3 significant figures. Now the zeros beginning the number are not counted as significant figures. The zeros beginning the number are not counted as significant figures. So we start to count from the number 6. Don't forget that we are asked to correct to 3 significant figures. So from 6 you begin to count 1, 2, 3. It ends at 7, but the next number is equal to 5. Take note that if the next number is equal or greater than 5, we consider it as 1 and add it to the number on the left. So when we count from 6, we have 1, 2, 3. It ends at 7, but because the next number is equal to 5, we take it to be 1 and add it to 7. Now 7 plus 1 will give us 8, and so we have 0.000688. That is how come we had 0.000688. Now II 63429.71. we have to correct this to 3 significant figures. And so we start to count from the number 6. 1, 2, 3. 1, 2, 3. The counting ends at 4. And the next number is 2. And because 2 is less than 5, we don't consider the number 2. And so we have 6, 3, 4, 0, 0. 6, 3, 4, 0, 0. So both 2 and the 9 are all given the digit 0 after counting our significant figures. After counting our significant figures. Take note that the 0.71, these are all given zeros, but the zeros after the decimal point does not matter. It doesn't count. And therefore, after giving 2 9 zeros, we ignore the 0.71. And so that is how come we have 6, 3, 4, 0, 0. Now rounding a number to the nearest whole number. Rounding a number to the nearest whole number. If we are asked to round a number to the nearest whole number, our concentration is on the number before the decimal point. The number before the decimal point. So let's take a look at this example. Correct the following numbers to the nearest whole number. A. 23.4. B. 324.97. C. 569.851. Now let's look at the solution. Considering A. 23.4. The number before the decimal point is 23. But immediately after the decimal point, we have a digit, and the digit is 4. Because 4 is less than 5, we ignore it. And so 23.4 corrected to the nearest whole number equals 23. Now, considering the example in B, 324.97. 324.97. The number before the decimal point is 324. But the number immediately after the decimal point is 9. That is greater than 5. And so we take it as 1 and add it to 4. And 4 plus 1 equals 5. And that is how come we have 325. 325. Now we consider the example in C. 569.851. So the number before the decimal point is 569. But immediately after the decimal point, we consider the number, and the number is 8. 8 is greater than 5, and so when we add, we take it to 1 and add it to 9. And when we add 1 to 9, we have 10. So we write 0 and give the 1 to 6. Now 6 plus 1 will give us 7. So we have 570. So we have 570. 570. Take note that the number before the decimal point is 569. But after the decimal point, the number 8, the first number is what we consider. And that is the number 8. And 8 is greater than 5. So we consider it as 1 and add it to 9. And 9 plus 1 equals 10. We consider it as 1 and add it to 9. And 9 plus 1 equals 10. So we write the 0 and give the 1 to 6. And 6 plus 1 equals 7. So we have 570. 570. Now the standard form. A standard form. A number expressed in the form m times 10 raised to the power n, where m is a number greater or equal to 1, but less than or equal to 10. M is a number greater or equal to 1, but less than or equal to 10. And n is an integer. And n is an integer. And n is an integer. Now example, 945000. 945000. Now for every whole number, the decimal point is at the end, is after the last digit. For every whole number, the decimal point is after the last digit. So with 945000, the decimal point is after the last 0. That means that the decimal point is here. And so now, converting this in a standard form, we move the decimal point to the left. So we have 1, 2, 3, 4, 5. So we move 5 times to the left, and that will give us 9.45 times 10 raised to the power 5. It is 10 raised to the power 5 because we moved 5 times to the left. If we move to the left, the exponent is positive, but if we move to the right, the exponent is negative. So we moved 5 times to the left before we had 9.45. So times 10 raised to the power 5. Now we realize that m is now 9.45, and 9.45 is greater than or equal to 1. It's greater than 1, but it's less than 10. It's less than 10. That means that 945,000 is equal to 9.45 times 10 raised to the power 5. And this is in the standard form. So this is the standard form. 9.45 times 10 raised to the power 5 is the standard form of the number 945,000. Now we consider 0.000000841. Now we can see our decimal point, and so we move our decimal point to the right. We have 1, 2, 3, 4, 5, 6, 7. So we have 8.41 times 10 raised to the power minus 7. Why is it minus 7? Because we moved 7 times to the right. Take note, I told you that when you move to the right, the exponent is negative, but when you move to the left, the exponent is positive. Example: evaluate the following, leaving your answer in the standard form. 625,000 times 0.00064, all divided by 0.00025 times 160,000. Now let's look at how best we can solve this problem. Now, given 625,000 times 0.00064 divided by 0.00025 times 160,000. Now we start with the number 625,000. So our decimal point is at the end, is after the last 0, and so we count to the left. We have 1, 2, 3, 4, 5, and that will give us 6.25 times 10 to the power 5. The exponent is 5 because we moved 5 times to the left. Now, considering 0.00064, we move to the right. Now 1, 2, 3, 4. So we have 6.4 times 10 raised to the power minus 4 because we moved 4 times to the right. And moving to the right, you have a negative exponent. Divided by, now 0.00025 in standard form, we move our point to the right. We have 1, 2, 3, 4. That is 2.5 times 10 raised to the power minus 4. Times now 160,000. So our decimal point is after the last 0. So we move it to the left. 1, 2, 3, 4, 5. So we have 1.6 times 10 raised to the power 5. Now 10 raised to the power 5 will cancel 10 raised to the power 5. And 10 raised to the power minus 4 will also cross out 10 raised to the power minus 4. So at the end we are left with 6.25 divided by 2.5. 6.25 divided by 2.5 times 6.4 divided by 1.6. 6.4 divided by 1.6. Now 6.25 divided by 2.5 is equal to 2.5 times, when we divide 6.4 by 1.6, the result is 4. And so 2.5 times 4 is equal to 10. 2.5 times 4 is equal to 10. Now we also have our decimal point after the 0, and so we count only 1 to the left, and that will give us 1.0 times 10 raised to the power 1. But 10 raised to the power 1 is equal to 10, and that is how come we have 1.0 times 10. Now binary operation. Binary operation. An operation on a non-empty set R consisting of real numbers is a rule which combines any two numbers. It's a rule which combines any two numbers xy belonging to R to produce another element. Now let us take a look at this example. Consider the set we have 0, 1, 2, 3, 4, 5 to be the elements of the set. Now 2 and 3 are elements of this particular set, and they are two different elements. When we say binary, binary means 2, and so binary operation is any operation that combines two elements to give another element. That is all. So 2 and 3 are all elements of this set. Now when we add 2 to 3, that is 2 plus 3 is giving us 5, and 5 is also an element. So we can see that we've added 2 and 3 together, and the result is 5, a single element. So binary operation is any operation that combines two elements to produce another element. So in this case, our addition is a binary operation. That's the addition is a binary operation because it is the addition that combines 2 and 3 to give us 5. There are other basic operations, and these are subtraction, multiplication, division, intersection, and union. Example, the operation are shown. This is the operation sign. The operation is defined on the set R of real numbers by A operated on B is equal to A plus B plus AB. So this is the rule. The rule says that if you are operating A on B, is equal to the sum, that is A plus B plus the product. So now let's look at the question that follows. Evaluate 3 operated on 5. 1 on 3 operated on 3 on 2. Now let's look at how best we can solve this problem. Solution. From the question, the rule has been given. A operated on B is equal to A plus B plus AB. So 3 operated on 5. When we compare 3 operated on 5 to A operated on B, we can see that A equals 3 and B equals 5. And the rule says that A operated on B equals A plus B plus AB. And so this is a matter of substitution. Wherever we see A, we substitute it by 3, and wherever we see B, we substitute it by 5. And in doing that, we have 3 plus 5 plus 3 times 5. And 3 plus 5 equals 8. 3 times 5 equals 15. Now 8 plus 15 is equal to 23. This means that 3 operated on 5 according to the rule is equal to 23. Now 1 on 3 operated on 3 on 2. So A equals 1 on 3 and B equals 3 on 2. So by substitution, we have A, that is 1 over 3 plus 3 over 2 plus 1 over 3 times 3 over 2. Now 1 over 3 plus 3 over 2 is equal to 11 over 6. Plus, now when we multiply 1 over 3 by 3 over 2, the result is half. You can see that 3 can cancel 3, and therefore we are left with 1 over 2. We are left with 1 over 2. So we have 11 over 6 plus 1 over 2, and this is equal to 14 over 6. This is equal to 14 over 6. And 2 goes into 14 7 times, and 2 goes into 6 3 times. So we have 7 over 3. This is an improper fraction because the numerator 7 is greater than the denominator 3. However, we can also convert this to mixed fraction. 3 goes into 7 2 times, so we have 2 whole number, and the remainder is 1. So we have 1 over the denominator. So 7 over 3 is equal to 2 whole number, 1 over 3. Now example, the operation is defined on the set R of real numbers by x operated on y is equal to x plus y all over xy, where x is not equal to 0 and y is not equal to 0. Now evaluate 3 operated on 5 and 1 on 3 operated on 3 on 2. Now we look at the solution. From the question, the rule says that if you are operating x on y, the result is x plus y. That is, you add the terms divided by xy. That is, you divide by the product of the two terms. So x operated on y is equal to x plus y divided by xy. Now 3 operated on 5 according to the rule will be 3 plus 5 divided by 3 times 5. And 3 plus 5 equals 8. and 3 times 5 equals 15. That means that 3 operated on 5 is equal to 8 over 15. Now 1 over 3 operated on 3 over 2. A equals 1 over 3. That is our x equals 1 over 3 and our y equals 3 over 2. So from the rule, x operated on y equals x plus y over xy. It means that 1 over 3 operated on 3 over 2 is equal to 1 over 3 plus 3 over 2, all divided by 1 over 3 times 3 over 2. And this is equal to, now we find the LCM of 3 and 2, and the LCM of 3 and 2 is 6. Now 3 goes into 6 2 times. So we multiply 2 by the numerator 1. 2 times 1 is 2, and that is how come we have our 2 here. Plus 3 goes into 6 3 times, and 3 times 3 is giving us 9. Now all divided by, when 3 cancels out 3, we are left with 1 over 2. So all divided by half. Now 2 plus 9 equals 11. So we have 11 over 6. Now when the division sign changes to multiplication, the denominator becomes the numerator, and the numerator becomes the denominator. So this is equal to 11 over 6 times 2 over 1. Instead of 1 over 2 is equal to 2 over 1, because the division sign has now changed to multiplication. Now 2 goes into 6 3 times, and so we are left with 11 divided by 3. So we have 11 divided by 3, and this is also an improper fraction, and we can convert this to mixed fraction. That is 3 goes into 11 3 times. The remainder is 2 divided by the denominator. So we have 3 whole number 2 over 3. Now let's look at these operations. Let's look at some types of operations. We have commutative operations. An operation defined on the set R of real numbers is said to be commutative if A operated on B is equal to B operated on A for all AB belonging to R. For all AB belonging to R. So for the operation to be a commutative, for the operation to be commutative, A operated on B must be equal to B operated on A. Now let's see. Example. The operation, this is the operation sign, is defined on the set of real numbers R by A operated on B is equal to A plus B plus 2AB. The rule says that A operated on B is equal to A plus B. That is, you first add the two terms plus 2 times the product of the two terms. That is the rule. Now show that the operation is commutative. Show that the operation is commutative. Now solution. From the rule, A operated on B is equal to A plus B plus 2AB. Let this be our equation 1. Now B operated on A will be equal to B plus A plus 2BA. But because addition is commutative, it means that B plus A can be written as A plus B. Multiplication is also commutative. It means that BA is equal to AB. Now let this be our equation 2. When we compare the two equations, equation 1, equation 2, we can see that equation 1 is equal to equation 2, which implies that A operated on B is equal to B operated on A. So if A operated on B is equal to B operated on A for all AB belonging to R, then it means that the operation is commutative. Then it means that the operation is commutative. Then it means that the operation is commutative. Now, associative operations. For every A, B, C belonging to R. So with the associative operations, we consider 3 elements, all belonging to the real number. All belonging to real number. Now, A operated on B into brackets, all operated on C is equal to A operated on B operated on C into bracket. Now, what I want you to look at here is the position of the bracket. On the left hand side, the bracket is enclosing A operated on B. On the right hand side, the bracket is enclosing B operated on C. Now, if the left becomes equal to the right, then it means that the operation is associative. Then it means that the operation is associative. Now, addition is associative on the set of real numbers. Why are we saying that addition is associative? Now, let's look at the illustration. Considering a plus b into bracket plus c, this is equal to a plus b plus c into bracket. If the left becomes equal to the right, then it means that the operation is associative. Now, for all a, b, c belonging to R, giving 2 plus 3 into bracket plus 4 is equal to 2 plus 3 plus 4 into bracket. Please check the position of the bracket at the left hand side and at the right hand side. Now the bracket first, let's solve. We are now solving the bracket first. So 2 plus 3 equals 5. So we have 5 plus 4. We have 5 plus 4. This is equal to 1. We add 3 to 4. The result is 7. So 7 plus 2. Now 7 plus 2 on the right hand side is equal to 9. And 5 plus 4 on the left hand side is equal to 9. That means that addition is associative. That means that addition is associative because 2 plus 3 into bracket plus 4 is equal to 2 plus 3 plus 4 into bracket. The left hand side is equal to the right hand side. Multiplication is also associative. That is, a times b times c is equal to a times b times c into bracket. Now, 2 times 3 into bracket times 4 is equal to 2 times 3 times 4 into bracket. Look at the position of the bracket. It's very important. Now, let's solve. Bracket first. So 2 times 3 is giving us 6. So we have 6 times 4. This is equal to 2 times, when we solve the bracket, 3 times 4 equals 12. So we have 2 times 12. That is how come we have 2 times 12 here. Now 2 times 12 on the right hand side we have 24. And 6 times 4 on the left hand side we have 24. So we can see that the left hand side is equal to the right hand side. That is why multiplication is also associative. That is the proof. Now, distributive operations. With the distributive operations, we consider two different operations. Now, the operation is distributive over this operation. If for all A, B, C belonging to R, A operated on B operated on C is equal to A operated on B, all operated on A operated on C. This is the distributive property. This is the distributive property. Now, let's take a look at this example. 2 times 3 plus 4 with the 3 plus 4 into bracket is equal to 2 times 3 into bracket plus 2 times 4 also into bracket. 2 times 3 into bracket plus 2 times 4 also into bracket. Now, let's solve the left hand side first. 3 plus 4 equals 7. Now, 7 times 2 will give us 14 on the left hand side. Now, we solve the right hand side and see. 2 times 3 will give us 6. And 2 times 4 will give us 8. Now, when we add 6 to 8, the result is 14. So, 14 on the left hand side equals 14 on the right hand side. Now, operations on rational numbers. Operations on rational numbers. We first take a look at the addition and subtraction. Now, given 2 over 3 plus 8 over 9, we are given 2 over 3 plus 8 over 9 to simplify. Now, how do we solve this problem? This is addition of fraction. The first thing we need to do is to find the LCM. And the LCM of 3 and 9 is 9. Now 3 goes into 9 3 times. And 3 times the numerator 2 will give us 6. Plus, because we have addition here. Now 9 goes into 9 once. And 1 times the numerator 8 will give us 8. So 6 plus 8 will give us 14. Divided by the denominator, that is 9. This is an improper fraction. How do we convert this to mixed fraction? 9 goes into 14 only once, and the remainder is 5, divided by the denominator. So 14 over 9 is equal to one whole number, 5 over 9. So if you simplify 2 over 3 plus 8 over 9, the result is 1 whole number 5 over 9 or 14 over 9. Now let's look at subtraction. Given 3 over 4 minus 5 over 8, with subtraction of fraction, we also find the LCM. And the LCM of 4 and 8 is 8. So 4 goes into 8 2 times. And 2 times the numerator 3 will give us 6. Minus 8 goes into 8 once. And 1 times the numerator 5 will give us 5. Now 6 minus 5 equals 1. So we have 1 divided by 8. We have 1 divided by 8. Now let's look at this problem. Given 3 whole number 3 over 5 plus 5 whole number 3 over 4 minus 7 whole number 1 over 2. This is equal to, let's simplify. These are all mixed fractions. And the first thing we do when we are given the mixed fraction is that we have to convert to improper before we can simplify. Before we simplify. Now 3 whole number 3 over 5. So we convert this to improper. So 5 times 3 will give us 15. 15 plus 3 equals 18. 18 divided by the denominator. So we have 18 over 5. Now we have our 18 over 5 here. Now 4 times 5 is 20. And 20 plus 3 is 23. So we have 23 divided by the denominator 4. That is how come we have 23 over 4. Minus 2 times 7 will give us 14. And 14 plus 1 is 15. So we have 15 over the denominator of the fraction. That is 15 over 2. Now we have 18 over 5 plus 23 over 4 minus 15 over 2. How do we simplify this? We have to find the LCM. And the LCM is 20. 5 goes into 24 times. And 4 times the numerator 18 will give us 72. So plus. Now 4 goes into 20 5 times. And 5 times the numerator 23 will give us 115. Minus 2 goes into 20 10 times. And 10 times 15 will give us 150. Now 72 plus 115 minus 150 is equal to 37. Don't forget, it's divided by the denominator 20. So you have 37 divided by 20. And the mixed fraction is equal to 1 whole number 17 over 20. Now multiplication and division of rational numbers. With the multiplication, we don't find the LCM as we did in the case of addition and subtraction. I repeat, with the multiplication of rational numbers, we don't find the LCM. We don't find the LCM as we did in the case of the addition and subtraction of rational numbers. So given 5 over 7 times 2 over 3, with multiplication, what we do is we multiply the numerators divided by the product of the denominators. And so 5 over 7 times 2 over 3 is equal to 5 times 2 divided by 7 times 3. Now 5 times 2 will give us 10. And 7 times 3 will give us 21. That means that 5 over 7 times 2 over 3 is equal to 10 over 21. Now let's look at division. 5 over 7 divided by 2 over 3. This is equal to 5 over 7. Now with division of rational numbers, we have to change the division sign to a multiplication sign. We have to change the division sign to a multiplication sign. And take note, when we are changing the division sign to a multiplication sign, the denominator of this fraction becomes the numerator, and the numerator becomes the denominator. So we have 5 over 7 times 3 over 2. Instead of 2 over 3, we have 3 over 2. Take note that the division sign has now been changed to multiplication, and that is why instead of 2 over 3, we have 3 over 2. Now we are back to multiplication, so we multiply the numerators and the denominators. So 5 times 3, then we have 7 times 2, and 5 times 3 equals 15, and 7 times 2 equals 14. So we have 15 over 14. This is an improper fraction, and a mixed fraction equals 1 whole number 1 over 14. 1 whole number 1 over 14. That is 14 goes into 15 once. That is the whole number, and the remainder is 1 divided by 14. Now, without using calculator, evaluate 2 whole number 7 over 8 times 1 whole number 1 over 5. all divided by 8 minus 2 whole number 1 over 4. Now B, 1 over 2 minus 1 over 4 plus 1 over 8, all divided by 3 over 16 plus 5 over 16. Let's see how best we can solve this problem. Now 2 whole number 7 over 8 times 1 whole number 1 over 5, all divided by 8 minus 2 whole number 1 over 4. This is equal to, now let's convert all the mixed fractions to improper before we simplify. So 8 times 2 equals 16, and 16 plus 7 equals 23. So we have 23 divided by 8. So we have 23 divided by 8 times, now 5 times 1 equals 5, and 5 plus 1 equals 6. So we have 6 divided by 5, all divided by 8 minus 4 times 2 is giving us 8, and 8 plus 1 is 9. So we have 9 over 4. And so we have 23 over 8 times 6 over 5 divided by 8 minus 9 over 4. Now 2 goes into 6 3 times, and that is how come we have 3 here. And 2 goes into 8 4 times, and that is how come you also have 4 here. Now all divided by 8 minus 9 over 4. This is subtraction of fraction, so we have to find the LCM. But take note, the whole number 8 is the same as 8 over 1, and so the denominator will be 1. The LCM of 1 and 4 is 4, so this is the LCM. Now 1 goes into 4 times, and 4 times 8 will give us 32, minus 4 also goes into 4 once, and 1 times 9 will give us 9. Now this is equal to 23 over 4 times 3 over 5 divided by, when we subtract 9 from 32, the result is 23. So we have 23 divided by 4. We have 23 divided by 4. Now when we look at the expression we have above the division sign, we have 23 over 4 times 3 over 5, all divided by 23 over 4. So 23 over 4 will cross out the 23 over 4, and we are left with 3 over 5. That is when 23 over 4 cancels 23 over 4, we are left with 3 over 5. And so the answer is 3 over 5. Now B, 1 over 2 minus 1 over 4 plus 1 over 8, all divided by 3 over 16 plus 5 over 16. Now let's simplify the numerator first. So we find the LCM, and the LCM of 2, 4, and 8 is 8. So 2 goes into 8 4 times. 4 times the numerator 1 equals 4. 4 goes into 8 2 times, and 2 times the numerator 1 is equal to 2. Don't forget, we have a minus here because of our minus. Now plus 8 goes into 8 once, and 1 times 1 will give us 1. So all divided by the LCM of 16, and 16 here is 16. Now 16 goes into 16 once, and 1 times 3 equals 3. 16 goes into 16 once, and 1 times 5 equals 5. So 4 minus 2 is 2, and 2 plus 1 is 3. So we have 3 over 8, and that is how come we have 3 over 8 here. 3 over 8. Now when we consider the denominator, 3 plus 5 is 8. So we have 8 over 16. So we have 8 over 16. That is how come we have 8 over 16 here. Now there is 3 over 8 divided by 8 over 16. Don't forget that as soon as the division sign changes to multiplication, the denominator now becomes the numerator, and the numerator becomes the denominator. And this is equal to 3 over 8. The 3 over 8 remains the same. Now times the denominator now becomes the numerator. So we have 16 over 8. We have 16 over 8. Now 8 goes into 16 2 times, and so 2 times 3 is equal to 6, and we have 6 divided by 8. That is how come we have 6 over 8. That's how come we have 6 over 8. That is how come we have 6 over 8. You can also multiply 3 by 16. You can also multiply 3 by 16, and that is 48. Then you divide it by the product of 8 and 8, that is 64. So 48 by 64, if you simplify, you will still get 6 over 8. You will still get 6 over 8. This is the end of our presentation on real number system. This is the end of our presentation on real number system.